So thank you for the invitation. And first of all, I'm not Wang, and she's my colleague, and as planned it, and she is going to give this presentation, but unfortunately, she wasn't able to be here, and so I will do it. And my name is Xin He, and Wang Yunting and me, and we both from the Chinese Chinese Academy of Science, and from the Institute of Computing Technology, and we are focused on the solution method, especially for the large and sparse linear systems. Actually, it's a very time-consuming part of the open form software. So that's the motivation, and we attend this conference. And in this work, and we would like to consider such a situation, and we want to solve a sequence of linear systems, not a single one, but a sequence. And but there are some common features of this sequence of systems. First of all, and all the coefficient matrix are symmetric and positive definite. If you think about the pressure Laplace matrix and from the open form, actually they are symmetric and positive definite. And the second one is that actually all the linear systems are not available at the same time. And not available at the same time. They are available one by one. Otherwise, if you have all the system, especially all the right-hand vectors at the same time, you can solve it very efficiently by using the block-Krylov subspace method. But that's not the topic of today. And here we are considering that we have to solve it one by one. If you think about this Laplacian linear systems from the open form, you can see that, especially for the nonlinear intuitions, in the open form we use a simple type nonlinear method, and we have to solve a sequence, a lot of linear systems, which are symmetric positive definite, and from the simple nonlinear intuitions and its variance, and also in the time fractional schemes for the Peso scheme and its variance. Also, the pressure equations are the most time-consuming part in all your simulation times. So that's the motivation, and we want to solve a sequence of linear system as fast as possible. And the platform is a very important thing. Actually, they change the solution method a lot, actually, and also the implementation optimization techniques, and also they change the solution method. And here, in this topic, we choose distributed memory clusters equipped with GPUs. Means that it is clusters, many computing nodes, but each node there are one or several GPUs. Actually, most of the computational power comes from these GPUs, is not from the CPUs. So in such the targets platform, and you have to make full use of the GPUs as much as possible. So if you have to solve the symmetric and positive definite linear systems, the first option came to mind is that is preconditioned conjugate gradient method. Actually, this is very beautiful and elegant, brilliant method. And here I just briefly recall it. And here the matrix M is a preconditioning. Actually, this is a very simple and very fast and efficient solution method, typically for the symmetric positive systems. Actually, after the PCG method has been built and many improvements and many variants have been proposed, for example, here we have this general two-level preconditioned CG method. Here, keep in mind that we are solving one system at this stage. Actually, if you compare with the standard PCG and the two-level PCG, you can see that the scheme looks quite similar, except that there are three other operators, such as M1, M2, and M3, and they behave as operators and in the intuition loop. So we call it the general two-level because that this is a very, very general framework. And in my next slide, you can see that all the information and the operators, and actually it comes from the techniques behind the domain decomposition, multi-grid, and deflation method, and extra. Okay, this is a formula of this two-level preconditioning CG method. And next slide, we will see that what kind of options or choices of these operators we can have. Actually, there are several, and it's not the full summary, but this is several very well-known and quite often used methods here. Actually, if you have the traditional and PCG method, actually, you only have this M1 operator, and you have all the other two operators as identity, so you don't have to do anything else. This is typically preconditioning CG method. And the second one is called additive correction. Actually, it's quite simple and very close to the standard one. If you see that it's a preconditioning matrix, M minus 1, and plus another correction matrix is called Q. Actually, as Q, we call it correction matrix because that this idea comes from the domain decomposition method, especially in the additive Schwarz preconditioning techniques. Actually, in the Schwarz scheme, actually you have this cost matrix and E actually as bottom of the slides, and then you construct the correction matrix and Q. Actually, this cost for the E matrix we call it cost matrix because the dimension is much smaller. Actually, generally in the domain decomposition is constructed from the cost grid, and you have this correction matrix and the Q, and you as a linear combination between the standard preconditioning and the correction matrix. And in such a way, you hopefully can accelerate the convergence rate of this PCG method. Actually, this is additive correction. And also, if you have a deflation is another very often used techniques. Actually, you have the projection operator P. Actually, the basic idea is that you have this projection vector, and you want to deflate all the smallest eigenvalues from the coefficient matrix and get rid of it. And then the effect condition number of the coefficient matrix can be bigger. So condition number should be smaller, and then you can have a fast convergence rate of the PCG method. This is the deflation method, the basic fundamental basics of the deflation method. Of course, we have this deflation variance for the deflation 1 and 2, and other some reduced balancing, something like that. But look at this one. Actually, all the options and the choices you have in these slides can be used directly in the general two-level preconditioning CG method. The key here is that how should you choose the, for example, for the correction matrix Q is additive correction. Actually, this is method we use in this presentation. And another one is the key is that how to choose the deflation vectors, deflation operator P. Since we use a two-level additive correction scheme in the two-level method, and you have from the previous slides you can clearly see that here we have a more clear see, and by compare the two-level AD method and the classic PCG method, you see that everything looks nearly the same, except one that in each loop, after preconditioning operator has been done, you have to do another correction. Actually, that's the only thing difference. But here, as I mentioned before, the key point is that how to determine the matrix Z, actually, and then you construct the correction matrix Q. That's a fundamental point. And another issue from the implementation point of view is that when you're applying this correction matrix, you have to make a multiplication with the correction matrix Q by a vector R. Actually, if you see that it's extra computational cost at each loop. So far we are thinking about solving a linear system, only single one linear system. But our objective is that we solve a sequence of linear system. But next slide, we will see that here, suppose that we have a sequence of linear systems. At the first system, we solve it by the standard PCG, And as you're solving this, we call it the seed system. We're solving that, and then at the byproduct of the project PCG method, you have this search direction vectors. That's small p, actually, we call the search direction vectors. And you save all the search direction vectors, and then you use that recycle. You use it as a recycle matrix. Actually, this is Z. And we move forward to the following systems, and we use this construct a Z matrix and to construct, to build our correction matrix Q. And then everything is known, and we have this two-level AD method, and we solve the second and the third, and continuously, hopefully, we solve more and more systems. So, actually, because the linear system changes and step by step, and fortunately, you can solve the several systems by using the same correction matrix. But unfortunately, and after some steps and some solutions, actually, it fails. It becomes inefficient. In that situation, you have to come back to the step one and rebuild this correction matrix, and then continually doing your job. So that's the story. That's a mathematical basis of our solution method for solving the sequence of several linear system of symmetric and positive definiteness, and we call it recycling and two-level AD method. So if you see this method, you can see that why it works. Because that when you are solving the first equations and you save all the search direction vectors P, actually the span of this all the search direction vector, actually, hopefully, the span can approximate eigenvalues, smallest eigenvectors corresponding to the smallest eigenvalues. Actually, at this point, actually, we come back to the deflation method, because that if you can choose approximate or have these eigenvectors which correspond to the smallest eigenvalues, and then you can get rid of it. And then the condition number is much smaller, and you can solve it much faster. But here is the basic thing that actually we are constructing the assertion direction vector and the correction matrix as the first equation, and the following coefficient matrix shouldn't change a lot. They shouldn't be the same, but they should slightly change. If it suddenly changes too much, and this doesn't work, unfortunately. Actually, this you can see that we recycle all the such directions from the city system. Actually, this method belongs to the class of augmentation method. But from the construction points of view, and you see this is purely algebraic. It means that you don't have to know the background and the physics behind this linear system. You just purely solve the first system, and then save the such direction vectors and use it as a correction. Okay, that's one. And for the construction of the E matrix, actually, it's very. Sorry, I have 2 minutes, and you see this construction is very easy because it's a diagonal matrix E, and most important thing is that we are applying in this correction scheme, and you have to multiply the correction matrix Q with a residue vector R. Actually, this is dense matrix multiplication by the vectors. It's very time consuming. However, in GPUs, actually, this can be very fast, very efficiently done in GPUs. That's a balance point, because we have extra computation cost, but which can be fastly and very efficiently executed on modern GPUs. And then the faster conversions can convert to the speed of the total solution time. Of course, and you have the, I will quickly come to the experimental results. And here we have X-over libraries and can be run and two different kind of architectures. But here in this talk, we mainly report the result on the high ground DCUs is AMD-like GPUs. And we plug in the X-over library in open form, and we solve it. And the benchmark a simple car. Actually, we solve the linear systems and of the pressure system. You can see that there is the smallest eigenvalue of the coefficient matrix. That's a very typical situation where the recycling method can work efficiently nicely. And if you see that when you are using the first PCG method to solve the first equations, it takes 200 iterations. And after that, you switch to the recycling method. You can see that the convergence is only iterations is only about half of that, and faster convergence. And this faster convergence finally transfers to the solution, the benefits in terms of solution time, because it's a dense matrix vector multiplication is efficiently done in GPUs. Actually, here is the total solution time of this 6 linear system. And you see that for the first one, we use standard PCG, and then we switch back to the recycling PCG, and the speed up in terms of the solution time is about 3. So it's 3 times faster than the standard PCG. Another one is a very typical area where the recycling method can work nicely is the Porous simple form, Porous medium. As is another benchmark, which is a typical benchmark in the open form tutorial, and you can try it. And here we solve, we use the same method and solve it very efficiently, and the speed up is around 2. So actually, I nearly finished this talk, and our ongoing work and the open questions right now is still that because we recycle all the search directions from the previous equations, so it can be very large. If it's very dense, it's a dense matrix and a very large size. So it's a consumption of the memory is very high. But in our experiments, you can use lower precision, for example, from double to single, and it works nicely, and it works. The efficiency doesn't change. However, the time consumption is half. But for the very large scale simulations, you still have to take care about this memory consumption because we recycle all the subspace. We don't pick them up. Okay. And another very important thing is that we have to determine or we have to predict that when this recycling method fails, because it's better to develop a smart method, and you can know that okay at this point, and you should move back to the preconditioned standard PCG method. Do not use this recycling method. But this is very challenging because in the whole simulation for the nonlinear simulations, it's difficult to determine when the coefficient matrix becomes quite different from the others. So that's all about this presentation. Thank you for your attention. Question, please.